Linear programming is a technique which is used in industries, organizations, manufacturing companies, production units, where the management would want to make a decision on how to maximize their profit or minimize the cost or maximize the production, right? So, what is the main objective of these companies? They would want to increase the profit, or they would want to reduce the cost, or they want to increase the production of their products. Now, any industry is set up with multiple resources such as people, machine, space, money, raw materials, right? So using this entire resources or setup, they want to figure out ways in which they can increase their profit. Now, say for example, they may want to increase the production of the products so that if they make more products, they can sell them more. Say for example, they can increase the production of their products so that the more the products they make, the more they can sell and the more they can make profits. So this is one way. Another way is they can probably reduce the time in making these products. Probably they want to manufacture these products faster so that they can sell them faster and make more profits in a short period of time. Or the other way is probably they want to buy technologically advanced machines which can increase the speed of making these products. Or they may want to hire more people who are required in building these products. Or they may want to invest more money, more capital so they can expand their business, or they can buy more raw materials and increase the production. There are also other ways, right? They may want to reduce the cost of making these products. One way is reduce maintenance cost. There are a lot of maintenance costs, right? It could be electricity, water, space, then the cost of raw materials. All of this they may want to optimize so that they can reduce the cost, thereby increasing the profit. Constraints. So, what are constraints? Constraints are limitations or restrictions. So, for any kind of industry setup or production setup, there is a limit to the number of people they can hire, number of machines they can buy, the amount of space they can use. There is no unlimited space, unlimited money. There is a limit to money, limit to space, limit to the number of people that can be hired. So, all these limitations are called as constraints. Now, like I said, there are multiple ways to optimize and increase profit or reduce cost. Now, management would want to find all those possible ways, right? All the possible ways by which they can attain their objective. The objective is to maximize or minimize the profit or cost, or it can be anything else, right? So, all that possible solutions are called feasible solutions. And out of those feasible solutions, there will be optimal solution. What is an optimal solution? A solution that gives you the maximum profit or the least cost. So that's the best solution or optimal solution. So what's an objective function? Objective function is a function that can be maximized or minimized. Decision variables, all of these resources that are used in a particular business or an industry are variables. We call them variables because they don't have a fixed value. They can be increase or decrease in all of these resources, be it people, machine, space, money. Let's solve a linear programming problem where we have to formulate LPP. To formulate LPP, what do we need? We need to first identify the objective function and then identify the constraints. So this is a 4-marker problem, right? So let's see what the problem is. Vishal consumes 2 types of food. So food A and food B, which requires minimum 8 units of protein, 12 units of carbs and 9 units of fat for his daily requirement. 1 kg of food A contains 261 units of protein, carbs and fat. 1 kg of food B contains 113 units of protein, carbs and fat respectively. Now food A costs 8 rupees per kg, food B costs 5 rupees per kg. Now we'll have to formulate LPPs. Now let's assume that X kgs of food A and there are Y kgs of food B. Basically, he wants to consume X kgs of food A and Y kgs of food B. Now, cost of food A per kg is 8 rupees. So, it is 8 rupees per kg of food A and 5 rupees per kg of food B. So, the cost is given. So, what will be the total cost? We'll have to add. add both of this. So it's 8 rupees per kg. So for x kgs, it's going to be 8x. It's 5 rupees per kg of food B. So for y kgs, it's going to be 5k. Sorry, 5y of food B. So now if you add both, this is what is going to be the total cost of his food A and food B. Now this is what is objective function. So what is objective function? Z is equal to 8x plus 5y. Now what we have to do? It has to be minimized. So the objective is to minimize Z. That is minimize the food cost. So this is the objective function. We'll chart out the types of food, because ultimately he has to decide how much he has to buy for food A and food B. Now let's chart out the constraints. So what are the variables? One is food A and food B, right? These are the main things that he wants to buy and on which he wants to get the minimum cost, food A and food B. Now what are the other variables? Other variables are protein, carbohydrates and fat. So food A contains proteins, carbohydrates and fat. Now they have given minimum requirement of all of these proteins, carbohydrates, fats that needs to be there in his food. So there should be minimum of 8 units of protein. So minimum is 8 units of protein, 12 units of carbs and 9 units of fat. This is the minimum quantity that has to be there in either food A or food B. Now in food A, how much of protein is there? It is 261 in 1 kg of food A. So 261 in food A, and in 1 kg of food B, it contains 113 units of protein, carbs and fat. Protein, carbs and fat. So there is 2 units of protein in 1 kg of food A, 6 units of carbohydrates in 1 kg of food A, and 1 unit of fat in 1 kg of food A. So now we have assumed that there are 8 kgs of food A. So which means it will be 2 into x, 6 into x, 1 into y. Similarly, in 1 kg of food B, there is 1 unit of protein. So how much is it for y kgs? You have to multiply by 5. Similarly for carbohydrates and for fat. So now we'll have to add this. And so we get 3 constraints here. So first one is 2x plus 1y. This is one constraint. And it should be within the total of the proteins that should be there in his food is 8 units. It can be more than that also, but minimum requirement, it's told here, minimum requirement is 8 units of protein, 12 units of carbohydrates. So when you say it's minimum, it can be greater than or equal to 8. So minimum is 8, it can be more than 8. This is our first constraint. Second one is carbohydrates, that is 6x plus 1y. This again should be greater than or equal to 12 units. Constraint 2. Third constraint is 1x plus 3y greater than or equal to 9. This is our third constraint. Then the fourth one is x should be greater than or equal to 0, y greater than or equal to 0. Because we can't have negative quantity of protein, carbohydrate or food A and food B, right? We can't have negative quantity of food A and food B. So we have arrived with the constraints and the objective function. We learned how to solve linear programming problem by obtaining objective function and constraints. Now we need to extend this problem to arrive at the actual value for objective function. For example, if we have to maximize profits, then we need to arrive at the actual values of the profit. So this is done using graphical method. So now let's take an example. Then we will explain step by step as to how to move forward with the problem. So we have a problem where objective function is given, constraints are given. Now using this, we are going to plot a graph. So step 1 is already done. Step 1 is to actually get the objective function and constraints. Now what is step 2? Step 2 is to get the points. Because if we have to plot a graph, we need the points and lines. So what we will do, we'll take the first constraint, which is x plus 5 less than or equal to 50. This is our constraint 1, right? So we will take the constraints, then we'll substitute x is equal to 0 and then get y. Then we will substitute y is equal to 0 and get x. So now with this you'll get 1 point xy here. Here also you'll get another point xy. With x as 0 and y 0 we'll get 2 points. Now similarly we'll take second constraint. Second constraint here is 3x plus y less than or equal to 90. So again we will substitute x is equal to 0 and you will get y. Then you will substitute y is equal to 0 and you will get x. So you'll get 2 points here again. So let's call this as point A, point B, point C and point D. So we have 4 points, right? Now we'll take these 2 points. Say we have a graph, right? We'll take this point. Say in this graph somewhere we get point A, then we'll get point B. We join the points and make it as a line. This is for one constraint, constraint number 1. Similarly for the second constraint, say you get another line, something like this, where this is point number C, where this is point C and point D. Now again we join the points. So this is constraint number 2. So now we have 2 lines. So step 3, what is step 3? Once we have plotted the graph, we'll have to find the overlapping, region. So there will be a common area between these 2 regions, right? So say this is one region and this is one region, right? Within this region, there will be a overlapping area between in this particular plane where this particular constraint is there and another plane where this constraint is there, right? There is overlapping region. Now if you see visibly here, this will be overlapping here. This could be overlapping, right? We identify the overlapping region and then call it a feasible region, right? Overlapping region is nothing but the feasible region. Then step 4. Now when you say there is a feasible region, it will have the vertices. Say assume that this is a feasible region. We'll use an example and demonstrate this. Assume that this is a feasible region. So it will have points. These are the end points or these are the corner points. So now we'll have to take these points. Say you get another 2 points E and F, for example. You take these 2 points E, F and C, right? And substitute. So step 4 is substitute the corner points E, F, C in objective function. And once you substitute, this is the objective function. Once you substitute, you will get the values of Z. And among these values, either you have to find the maximum value or minimum value based on the question. If they've asked us to maximize, then you have to find the greatest of the values. If it is minimized, then you have to find the least of the values, right? So, and that value that you get is nothing but the optimal solution. Now let's take this example and execute all of these steps. So let's take this constraint 1. What we have to do? We'll have to substitute x is equal to 0 and get y. So when we substitute x is equal to 0, this equation is going to become 0 plus y. Now instead of taking this less than, we will make it as equal to, so that we get a point. So this will become 50. So when x is 0, y is 50. So what is the first point we have? 0 and 50. Let's name it as A. Now let's take y is equal to 0 for the same constraint and substitute. So x plus y is 0 is equal to 50, which means x is equal to 50. So we get the point, let's name it as B. We'll get it as 50, 0. Let's do the same thing for the second constraint. Second constraint is 3x plus y less than or equal to 90. So this is our second constraint. So we are going to again take x is equal to 0. So what do you get? 3 into 0 plus y equal to 90, which means y is equal to 90. So what is our third point? 0 and 90. Now we will take y is equal to 0. So we get x, 3 into x plus y is 0 is equal to 90. So we get x is equal to 90 by 3, which is 30. So what is our point? Fourth point, it is 30 and 0. So we've got 4 points. We have got the points from both the constraints. Now step 3. Step 3 is to plot these points. Plot points and get feasible region. So roughly I'm going to draw this graph. So let this be an origin or O, which is 0, 0, right? So the points are 50, 90, 30. Okay, let's get as units of 10. 10, 20, 80, 90. Similarly, we can plot over here. Let's take the first point, 0, 50. So x is 0 and y is 50. So this is going to be the point. let's call this as point A, which is 0, 50. And the second point B is 50, 0. So 50 on the x-axis and 0 on the y-axis. So this becomes point B. Now we will have to join these points. So now what does this line represent? It represents this particular constraint number 1, which is x plus y less than or equal to 50. Now we'll plot the third point, which is 0, 90. 0 on the x-axis and 90 on the y-axis. So this becomes a point C. The fourth point is 30, 0. So 30 on the x-axis. So this is the point. Let's call it as D. Now let's join these points. So we get another line which is representing constraint number 2, which is 3x plus y less than or equal to 90. Now there are three things that we have to remember here. Whenever the constraint has less than, right, we'll have to shade. Now we'll have to do the shading, right? So let's take the first constraint. We'll have to do shading for each of the constraints. Let's take the first constraint, that is x plus y less than or equal to 50. Now, since there is less than or equal to, the shading will be inwards towards the origin. That means you can assume that you're going to color this entire portion starting from that line. Right? We'll shade this entire portion. So this is one region which represents this particular constraint. X plus y less than or equal to 50. So anything, all the set of points below this line represent this particular constraint, or this is one region. Now similarly, we'll shade for the second constraint, this one. Now this is also less than or equal to 90, which means it is inwards. The shading should be towards the origin. This is the origin. So let's take a different color so that it becomes easy for us to identify. So I'm shading here. Notice that the shading starts only from that particular line, this line, right? Now you have to observe the region which is overlapping. So you have one region here and you have one region here. Two areas are there. Find the overlapping area. So where both the lines or both the shaded colors are maximum. So if you see, the region is this one. This is the region. This is called the overlapping region. Nothing but this is the feasible region. Now we'll have to identify the corner points. So we have point A here, point B here. This is the intersecting point. So this point we'll have to find out. If you plotted this accurately using a graph paper, then we'll get the exact values of this 30, around 30, and this is around 20. So I can say the point is 20, 30. The point is 20, 30. 20 on the x-axis and 30 on the y-axis. So this is our point. Let's name it as E. Right? Now we have three corner points, A, E, and D. And we also have origin also as one of the corner points, because this entire thing is one area or one region, one feasible region. So we'll have to consider even this as a point. Basically all the vertices or all the corners of that particular region is called as a feasible solution. So basically all the corner points of this particular feasible region is what we are going to use to calculate optimal solution. So as part of step 3, we've got the feasible region and corner points. Right? We have 4 corner points. Now what is step 4? We'll have to substitute corner points into objective function. Right? Each of these points we will have to substitute. Now what is the objective function? 60x plus 15y. Let's substitute all the points one by one. Let's take point 1. Say point 1 is, let's write the corner points here. So A, 0, 50. Then next point is E, 20, 30. Next point is D, it is 30, 0. And origin O, which is 0, 0. So these are our corner points. Now let's take point First point 0, 50. Let's substitute. What do we get? We'll take this as x and we'll take this as y. So 60 into 0 plus 15 into 50. What do we get? 0 plus 750. So answer is 750. Now let's take the second point, which is 20, 30. We'll take 20, 30. Let's substitute. 60 into, this is our x and y. 60 into x is 20 plus 15 into y is 30. So what do we get? We get 1200 plus 450, which is 1650. Let's take the third point. 60. Third point is 30 and 0. Point D. So x is 30, y is 0. So we get 60, we get 1800 plus 0, we get 1800 as the answer. Now, let's take the fourth point, which is origin 0, 0. So it's going to be 0 because when you're going to put x and y as 0, this is going to be 0. Now, the last step. So now, what do we call all of these z values that we have got? We've got 1, 2, 3, 4. We have 4 values of z. These are called as feasible solutions. Feasible solutions. Basically, these are the solutions for each of these variables. Now, out of these feasible solutions, we'll have to find the best solution or the optimal solution that will give maximum value for z. Suppose it was maximize profit. So, which of these values will give you maximum profit? Right? We'll have to find the biggest of these numbers. Now, you have 750, 1650, 1800 and 0. So, which is the maximum? 1650. This is, sorry, 1800 is the maximum one. So, we'll have to pick this is the biggest. So, our optimal solution is 1800. And what are the values of x and y? Values of x and y. Optimal solution is 1800 at x and y. What is x? 30 and 0. So at this point, when x is 30 and y is 0, we get the best or optimal solution, and the value of that optimal solution is 1800. So we have maximized z here. We have maximized the objective function. So to summarize, step 1, we should have the objective function and the constraints. Then step 2, we should have arrived at the points. All the points by substituting x and y in each of these constraints, we'll get the points. And step 3, we are going to take all of these points and plot it in the graph. And then we are going to shade it based on the limit, based on whether it is less than, greater than, equal to. So if it's less than, the shading will be inwards towards the origin. If it was greater than, the shading will be outside, away from the origin, something like this, right? Then you will find the overlapping region where all the points meet. Now in this case, this is the maximum shaded portion where both the shading is overlapping. So this region is called feasible region. Once we obtain the feasible region, we'll get the corner points of the feasible regions. Use those corner point values, substitute in the objective function, we'll get number of feasible solutions. Once we get feasible solutions, we'll either pick the maximum or minimum based on the question, and we'll get the optimal solution.